Hello everyone, this is the Algebra 2 and of course review for Chapter 4b, and we will be talking about function operations and inverses in this video. Alright, so I'm going to talk a little bit about operations on functions. You actually have 4 different types of operations. You have addition, subtraction, multiplication, and division. The only one that you really need to pay very close attention to is subtraction. When you are subtracting your functions, make sure that you are subtracting everything in that second function. So if you have more than one term, this is going to wind up being negative x and then minus 2, because you have to subtract both of these terms, and then of course it turns into 5x minus 2. When you are adding, remember you add coefficients, so perhaps you are taking 2x squared and 3x squared. That's going to wind up being a total of 5x squared. But if you are multiplying 2x squared times 3x squared, you multiply 2 times 3, you get 6, and then you do x to the power of 4, because you do 2 plus 2, because you have to add your exponents on that one. Other than that, sometimes they might leave it an x. Sometimes they might want you to plug in a value for x and substitute and find the output. Okay, now while you are just kind of introduced to an inverse function in this particular section, it kind of carries throughout all of the book for all the different types of functions. So this in particular is what a function and its inverse is going to look like. Remember, inverses have a line of symmetry. It is a diagonal line. It is y equals x. This right here, this blue line, or not blue line, but blue curve, is a square root of x. And the inverse of a square root, of course, would be the inverse function square. So this is x squared. The domain and the range are going to match. Vice versa, the range and the domain match as well. I'm going to talk about that over here. So whenever you have the domain of one function, that domain is going to wind up being the range of the inverse. They flip-flop. The range of your original function is now going to be the domain. And the reason why is because you are swapping the x and the y. You're swapping the x and the y. So the domain, which stands for your x, is now going to become the y value. So here's another kind of example right here using coordinates. If you wanted to find the inverse of 2, 9, you would just flip-flop them and say the inverse would be 9, 2. Here's another one where it's graphed with the coordinates. Red line, blue line, you can see that line of symmetry right here. That's not perfect, but it's pretty dang close to it. But anyway, all you have to do is swap the x and the y coordinates, and you can find the inverse. If you are trying to find the inverse, if you are trying to solve for an inverse from a function, you have to replace f of x with y and then do the magic thing. You swap your x and y, and then you solve for y. We're going to do some practice with that. But before I do that, let me show you just a handful more. This looks like this is a cube root function here, and then the inverse would be x to the power 3. This one is yet another radical, so it's the square root of x. It's just been translated left 2, and then that means that the parabola is going to be translated down 2. Remember, the domain and the range do switch positions. And this blue one right here is a quadratic function, but the red one, on the other hand, the inverse is not a function, but that's what it would look like if you graph the entire thing. One thing that I did not mention is a composition of functions. That is a function operation, but it's different. You're not adding, subtracting, multiplying, dividing. What you're doing is you are actually taking one function and substituting that function into the other. You could have a function itself substituted, or you could just actually have a value. And if that's the case, let's say you were trying to find g of f of 3, you would substitute 3 into your f function, and whatever you get for that, you would plug that into the g function. That's how you do a composition of function. This is kind of visual of the composition. Whatever you plug in here is going to wind up being the output, will turn into the input of the next function, and then final answer is going to be the output of that second function there. One last thing, you need to figure out what a one-to-one function is. If you don't remember, a one-to-one function is where you can qualify a function as a function, and the inverse of that is also a function. So the way you can do that is you can either swap your x and your y variables, or you can run something called a vertical line test. So a vertical line test will tell you that it's a function. So vertical line test, just to see if it's a function, and that basically is just like this invisible line that goes across from left to the right, and as long as your function only touches it in one spot, then it's going to be considered a function. If you rotate that line and you make it a horizontal line, you can see this red horizontal line here. If you go up, down, and as long as that function is only touching in one spot, if it intersects in more than one place, it's no longer. So see how that only intersects in this one place here? It doesn't matter how far up or down it will be, it will only intersect in one spot. So that's going to be a one-to-one function. This one, on the other hand, does pass the vertical line test, but it does not pass the horizontal line test. So this is a function, but it is not one-to-one. Something that is an example that is not a function is going to be like a sideways parabola, such as, where did it go? Where did it go? Right here. So this red sideways parabola is not a function. The blue one is, on the other hand. So that means that it will not pass the horizontal line test, so it is not one-to-one. Let's go ahead and work on some problems. All right, so this one is what we call a composition of functions. You can see that we're taking g of x. So we're going to take this function right here, and we are going to plug it into the f function, and we're going to substitute this blue x for this whole thing in yellow. So this is going to be a little bit more difficult because it's going to stay in x. But what I like to do, instead of writing an x here, I'm making a really big space for this whole yellow part right here. And I'm going to substitute this with the cube root of 5x plus 1. You're going to have to simplify it a little bit. Let's see what happens. So 4 times this whole radical is just going to be 4 cube root of 5x plus 1. You're not allowed to multiply inside the radical. It's like an invisible barrier. So looks like that's the only thing I can do. So it is D. See what it does right here? It gives you like 20. So if you didn't know about that barrier right here, you're going to pick A or B, which is incorrect. All right, this next question right here says, what's the inverse of this function? Notice how the top two do not have calculators, so please be prepared. You're not going to be able to have Desmos the entire test. All right, first thing you're going to do is replace g of x with y. Then you're going to swap x and y. If you don't swap your x and y, you're not finding the inverse. After you do that, your main goal is to get y isolated. So I'm going to subtract 5. A lot of this will not simplify. Whenever you divide by something, make sure you divide the entire side. Let's see if I can eliminate anything. Well, I definitely know it's not going to be plus 5, so A is out. It looks like I think B is the right answer. No, these are in the wrong order. Same. So B is the correct answer. Okay, this question's like a two-parter. It's asking you to find the inverse, but then it's asking you to figure out what the domain of the inverse is. So let's tackle the first part. Let's write over here on the side. I've got 1/2 x squared plus 1. That's supposed to be equal to y. Sorry, I switched sides here. I'm going to go ahead and swap the x and the y here. And I'm going to get y isolated. Okay, when you get rid of this 1/2, you are supposed to multiply both sides by 2. That means all of this side. Okay, so I have 2x minus 2 here. And then to get rid of the y squared, you have to take the square root of the entire side. Now here's where you got to be careful. It says you're finding the inverse of the function only where x is greater than or equal to 0. That's positive numbers. So remember when I told you to take the square root of both sides? You're supposed to have a positive and a negative, but it's limiting that right there. So your domain is limited only to the positive numbers. So I can immediately cross out A, B, and C. You can answer this with just the equation part of it, but I want you to understand that the reason why your domain in this is limited to 1, it's because when you graph this, it starts here at the origin and it goes out this direction. The range, oh, sorry. It starts at the origin, but you see this actually means up one. So if your range of this one is 1 or above, same thing here. The way that you can get around this is that you can state that everything underneath the square root has to be greater than or equal to 0. So you can see that x is forced to be greater than 1. Okay, in this next one, you're adding them together, so you can just simply like match like terms. I'm just going to color code here. When you're adding terms, you don't change the degree. So I'm going to start with x to the third. It doesn't have a match, so all of those check off. 2 plus 1/2 is going to be 2.5, and 2.5 as a mixed number is 5/2. So 3/2 is out, 3/2 is out. So it's either going to be B or D. So it's going to be one of these two. And then 3 minus 4 is going to be -1. That's a no. So it has to be D. All right, lots of practice for inverses here. First thing you want to do is change that f of x to a y, and then we're going to swap our signs and then isolate y. Divide by 5. Final answer, x over 2, or x plus 2 over 5, and you can change that y into your function, inverse function notation. All right, this is a composition of functions, but it's going to be a little different because you're not substituting the entire function. You can just substitute 65. You're just using the same function twice this time. So 65 minus 1 is 64, and the cube root of 64 is 4. So I can replace this part with 4. I'm going to substitute a 4 this time around. I cannot simplify it because I can't go any further than the cube root of 3, and that's it. Just a quick reminder, you can actually type in f of x into Desmos, and then on the second line, type this entire code, and it will do that for you. The only problem is that it will give you the answer as a decimal. So it, sometimes you do have an advantage of just doing it on your own without a calculator. So I think the easiest way to explain this one is that I'm just going to write these as coordinates. Now pay attention, this is actually the inverse notation. So the inverse coordinates are -7, 0, -3, -1, 2, 2, 4, -2, and 5, -3. Okay, this is your x, this is your y. So if they want to find f of -3, that's basically like, let's go ahead and flip it around and figure out the other one, or the original one. So that's going to be 0, -7, -1, -3, 2, 2, no changes there, -2, 4, -3, 5. All right. So once again, it's basically like if you have the original function, what do you get? What's your output when you plug in -3? Well, when I plug in -3, I'll wind up with +5. So the answer here is 5. You just got to remember, if you want to do it super quickly, you have to remember that the domain is the range of your inverse. So this is the domain of your original, which is going to be the range of your inverse. So if you just find the -3 in the range, domain is going to be the answer. All right, so for the last one, it's asking us to classify the following as a function, one-to-one, or not a function. So what I'm going to do is I'm going to first check to see if it's actually a function. So I'm going to take this, I'm going to show you what it's like to check using the vertical line test. So as you move it from left to the right, you see where that blue function only intersects at that one place, okay? It doesn't matter. It looks like it might eventually go straight up. It will not. It looks like it's getting closer to the x-axis. It doesn't ever touch it. So it follows a function rule. So this one's a function. Let's check to see if the circle is a function or not. Absolutely not. It hits it multiple places. So this one's kind of out. So this last one is just not a function at all. If it's not a function, then it can't be one-to-one. Now I'm going to delete this, and then I'm going to check to see if it's 1 to 1. I'm going to create another line, but this time it's going to be horizontal. And I'm going to grab that, and all right, now looks like it's going to hit. It doesn't, because it's asymptotic. What it does is it gets closer to the x-axis, but it never actually like repeats the same point. So this is good. It's going to pass the whole time. So the first one is definitely going to be 1 to 1, but the second one is not a function at all. Okay, so one last time, if it's a function, it'll pass that vertical line test. There's no outputs or y values repeating for the same x value. And then vice versa, horizontal line test, you're not going to have any x values repeating for one particular y value. So let me know if you've got any questions.